Welcome to the ME140 IC Engine Lab. I'm going to go over a couple of brief descriptions of this lab. And so up to this point we've been looking at combustion in an open volume. In the IC engine we're going to be looking at combustion within a closed chamber. Okay, and the combustion process is actually going to do work against the piston, which is going to drive the piston down and create power. Okay, inside the internal combustion engine, this particular engine is a 4-cylinder. It's a 1986 Pontiac 4-cylinder turbocharged engine. It's kind of old, but it's actually, for its day, was very cutting edge. Port fuel injected. It's got all the components that a modern engine has, but it has an ignition system that we can easily adjust. So that's why we like the older engine. The engine itself is coupled to a dynamometer. This blue device is called an eddy current electric dynamometer. We can apply a load to the engine, similar to if you were in a car driving up a hill. The steeper the grade, the more the load, or the more people in the car, the more the load. Using this dynamometer, we can apply a load to the engine and actually get it to make more power. Obviously, when you go up a hill, the RPM goes down, so we can limit the RPM and we can apply load. We're actually also able to vary the throttle using a controller out in the hallway, and we'll go over that in a couple of minutes. Basically, in this engine, we're looking at two different things. We're looking at the cylinder pressure inside cylinder number 2 using a pressure transducer. And so we're able to see real-time the cylinder pressure through all 4 strokes of the Otto cycle. We're also looking at the thermal efficiency and thermodynamics of the engine. We have 16 thermocouples on this engine. We're looking at the air as the air goes through the engine. It comes into the air intake, goes through the turbocharger. I'll cover what a turbocharger is in a minute. But the air goes through the turbocharger, comes out, goes through a air-to-air heat exchanger called an intercooler. And then it goes into the engine, goes through the combustion process, and exits through the exhaust manifold, through the turbo, the exhaust side of the turbo, and then out through the exhaust. So through that whole flow, we're looking at 8 different thermocouples reading the temperature as it goes through the process. We're also looking at the coolant and water flow of the engine. An internal combustion engine makes a lot of heat. There's a lot of frictional loss, a lot of parasitic loss on the combustion process, and the frictional loss of the metal components working against each other. So because of all that built up heat, we need to cool the engine. And by doing that, we have a recirculating coolant system. On a normal car, we have a radiator and a water pump. The water pump circulates the coolant through the engine, through the radiator, to get cooled off and back into the engine. In this particular laboratory, we have it set up where we have a water-to-water heat exchanger instead of a radiator. So we're able to much more closely measure the amount of flow and the temperature differential between in and out. On this side of the engine, we came to the other side of the engine so I could show you a couple other components. Here we have the turbocharger. A turbocharger is a compressor. And the compressor side is here, and the turbine side is here. As the exhaust comes through the exhaust manifold, it goes across the turbocharger, the turbine, and it spins a turbine inside, and then the exhaust goes out the tailpipe. That turbine spins a shaft inside the turbo, and it spins the compressor side, so that where the air comes in, it compresses the air and puts it out as a compressed volume. Following the exhaust flow, we have a catalytic converter right here. A catalytic converter is a device created to reduce emissions inside of an engine. The fuel that we use in an internal combustion engine, up till now in our ME140 we've been using methane and methanol. The internal combustion engine uses regular gasoline. It's super unleaded gasoline or octane. So the burning of that, the combustion process, creates a lot of harmful chemicals and gases, in particular NOx. The catalytic converter is actually a device created to reduce the emissions and convert them into less harmful chemicals. So in our laboratory setup, we can actually, using the Hariva gas analyzer, and we'll go over that in a minute, we can actually sample the emissions before the catalytic converter and after the catalytic converter using the solenoid. We have a switch out in the hallway right next to the gas analyzer. We can actually look at the efficiency of the catalytic converter. Okay, this is a cut-apart turbocharger that we have. On this side, you can see the exhaust comes in and spins the turbine. And on this side, through a common shaft, we're spinning the compressor side. So the air is drawn in here, and the compressed air goes out. Okay, this is a duplicate, a twin to the engine that we have running. We have it cut apart so we can actually see what happens inside the engine. Now, one of the things we can do with this engine is we can adjust the ignition timing. So we can adjust the relationship to the piston as it's coming up when the spark occurs. Okay? So when we advance the timing, if we're watching this number 1 cylinder, as the piston comes up, if we advance the timing, the spark occurs earlier, like right here. As the piston's coming up, if we're at baseline timing or the traditional timing, it might occur here. And as we retard the timing, which means it occurs later, it might occur closer to top dead center. Ignition is always going to happen before top dead center, but we can adjust it so that it can occur earlier or later than our baseline timing. Okay, this next program that we're going to use is going to look at the pressure inside the volume, inside of our cylinder. Up to this point, we've been looking at combustion processes in an open volume and in a closed chamber. Keep in mind that in an internal combustion engine, the combustion process occurs inside of a variable volume closed chamber. So as the combustion process occurs, the combustion process does work on the piston by pushing it down, thereby increasing the volume of the chamber. So using our pressure trace that's fed by our cylinder pressure transducer, we're able to look at the cylinder pressure real time throughout the entire 4-stroke Otto cycle. So looking at this trace, I'll briefly describe what each process is. We're going to start at bottom dead center, and this is our compression cycle. Right about here we reach top dead center, and our combustion process occurs. That's where the work is actually done on the piston. Now we reach bottom dead center again, and the exhaust valve opens. The piston goes up, pushing out the exhaust, and then right here at this drop, at top dead center, we close the exhaust valve and open the intake valve, and we draw in the air and fuel, and the entire process restarts.
To examine the effect of the catalytic converter and changes in ignition timing, we are going to compare the emissions of 4 samples. First, to look at the effectiveness of the catalytic converter, we will sample the exhaust gases before and after they pass through the catalytic converter. We're going to do this with the baseline or traditional ignition timing. Then, to understand the effect of the ignition timing, we're going to look at the emissions before the catalytic converter while we run the engine with an advanced and a retarded timing. As we can see in this graph, the catalytic converter completely eliminates all unburned hydrocarbons from the exhaust. Advancing the timing increases the levels of unburned hydrocarbons, while retarding the timing decreases the level of unburned hydrocarbons. The catalytic converter is less efficient in reducing carbon monoxide in comparison to the unburned hydrocarbons, but as we can see, there is still a significant reduction in carbon monoxide after the catalytic converter. Changing the ignition timing either way reduces the carbon monoxide emissions compared to the baseline timing case. The catalytic converter also significantly reduces the nitrous oxide compounds, or NOx, in the exhaust. Similar to unburned hydrocarbons, the NOx concentrations in the exhaust increase as the timing is advanced and decrease as the timing is retarded. As an exercise, discuss and explain these trends.